My name is Marcell Fehér. My supervisor is Daniel Lucani, and we are from the ECU department. As you can see from the title, I'm also working with IoT data. And my motivations for this is very similar than the previous presenters who are also working on IoT data. Basically, the problem is that an exponential data growth is predicted for data that's coming out of IoT devices from many, many sources. You can see the same prediction, and nowadays you can already see that this prediction turning into reality. The issue with this is basically always when there is a growth in something, there are several ways to manage the growth. And typically what we do is we extend the infrastructure capability to manage it, but often it's very expensive and sometimes impossible to do it when the data or the problem scales exponentially. A better approach than that is to try to increase the efficiency of, in this case, the data transfer and storage to decrease the data growth rate to something that's manageable. And actually, data compression is a really good tool for this for multiple reasons. First of all, it can be applied quite transparently, at least for data transmission. So we don't need to come up with better protocols. We don't need to come up with completely new data formats to be able to be more efficient with data transmission. Applying compression doesn't really need to, involve changing anything in the other layers, in the application layer or anywhere else. You kind of just apply it, and it's a transparent tool that just helps. Also, with lossy compression, we have another tool, or we have more control in our hands with precision versus data size trade-off. So if you don't need full precision of the data, then we can go with higher compression by introducing lossy compression methods. Also, IoT data is highly redundant, so it's really an ideal ground for data compression and trying to attack this problem with compression. With these methods, we can improve the whole life cycle of the data, so transfer, storage, and analytics as well. About the context, in our research group, we are exploring this new compression technique called generalized deduplication. I'm not going to go into details of how it works because Nilufa did it already, if you remember, with the colorful shapes. Basically, we extract most of the information, which was the shape in that case, to this common basis and then deduplicate them and keep the difference in the so-called deviations, which was the color in that space. So this is a very general technique, and it's kind of customizable with this user-given transformation function. So it can be tailored for the problem. It can be tailored for the actual data set that you want to compress, that you're working on. So in terms of my research, I'm a second-year PhD student, and I have a couple of different topics that I have been exploring and I'm planning to explore during my PhD. My biggest project is the first one, so using generalized deduplication for power consumption readings, basically compressing the data packets that are uploaded by smart electricity meters that are in your home and in office buildings. Reducing the overall network traffic from these millions of meters, and also making sure that that private information is not being leaked about the consumption. Then the second one is trying to find a way to execute queries, so data analytics, directly on compressed data, which would enable exploratory analysis of much larger data sets than currently possible, either in a browser or any other memory limited environment. And also it can speed up query processing. It can answer queries that span much larger data sets in the same amount of time when applied properly. Two very similar or like joint problems with these is first designing a generalized deduplicated format, so data format that can store data that is compressed with this technique. And I'm working on this this file format that supports a multitude of transformation functions and all sorts of flexibility that is necessary for different kinds of generalized deduplicated compressed data, and also provides random access with low overhead. So you can decompress only a part of the file without having to decompress the whole thing. Also, I'm also trying to expand the whole generalized deduplication concept at all. So moving from the very basic idea and the basic implementation to more advanced techniques like this, what I call a pattern GD, where we move the position of the bases and the deviations to where we expect the most highly varying bytes, as opposed to simply processing the chunks right after each other and not really caring about the underlying structure of the data. So that's one technique, and the other technique I would like to explore in the near future is whether if the data set is highly redundant, then it might have a couple of these generalized deduplication bases that are much higher frequency than other bases. And in that case, we could take these bases out of the data representation, include it in the compressor and the decompressor, and not have to transfer anything about them or almost anything about them on the wire. Right, so let me start with the main project that I've been spending most of the time in the past like 1.5 years is power consumption readings. So the typical way it works is that we have a utility provider, like an electricity provider company, who has a server backend, and they remotely configure these smart meters that are in your home, and they have like usually a 2G data connection where they can send information back to the head-end system, so-called. And these informations, or these pieces of information, is basically your power consumption readings that the meters are recording typically every 15 minutes. And at some predefined time intervals, they encode these readings into a data packet and upload it to the head-end system, to the utility provider. So when these systems were first deployed, they were usually set to, as I mentioned, to record every 15 minutes. And originally, they uploaded a single data packet with a whole day's worth of measurements once a day, like around midnight. Nowadays, the trend is that the power companies want to receive this information more granularly and more like closer to real time, so lower age of information, which imposes a couple of problems. First of all, the compressors that are being used right now, they were designed for compressing a whole day's worth of data, and they are not really efficient in terms of data size reduction if there are only like one or a couple of readings are uploaded at once. And also it turns out that they leak a lot of information at the size of the compressed packet about the compression. So if there is an attacker who can only passively observe the encrypted traffic that's coming out of the smart meter, they can infer many things about the consumption and the patterns of electricity use of the private customers. So that's really an issue. So my task is here, and my project is to compress these APDUs, these data packets that are uploaded from the smart meter to the head-end system, compress them at the smart meter side and decompress them at the head-end system side before they are being processed in the system. This obviously has to be a lossless compression because the billing of the customer is based on this data, so we cannot afford any imprecision. And as I mentioned, there are two important factors here. First is obviously data size. So we want to decrease the amount of data that's transferred over the network. And the other one is privacy. So we have to come up with compression methods that do not enable any attacker who is listening to the conversation or who is looking at the data sizes, the packet sizes, to infer, for example, when you're usually at home, or to be able to infer what's your schedule, daily schedule, when do you wake up, when do you leave the house, when do you come back to the house. This is getting more and more of a problem. As I mentioned, the protocol itself, it includes a couple of compressors, but they are not really suitable for the new use cases. So I have a couple of concrete tasks here. First of all, measure everything and evaluate everything in this new setup where we upload where we upload electricity readings hourly or maybe even instantly. So immediately as it's measured, it's being uploaded. It's kind of a new territory for the whole industry. So they're changing in the meantime. So nowadays, from receiving data once a day to receiving data once an hour, or receiving every single measurement immediately. So in this project, I've proposed a couple of compressors based on generalized deduplication. I won't really go into details here. A couple of them has already been published, and I want to spend the next few months working on the multi-stream and lookup table approach. I have 2 papers published, 2 papers submitted right now, and currently working on a journal paper that's an extension of these papers. And basically summarizes all the work that I have done in this project. I have a couple of results here. I'm sorry, these have been copied from different presentations and different papers, so they are not super consistent with each other. The thing I want to show here is that the orange line here is the legacy compressors. So the compression rate, as there are more and more data, more and more readings being compressed together and uploaded together. And the trend is that as we go lower, so as we want to upload more frequently, the compression rate and really the data size reduction quality of these compressors drastically go down. While the green one, which is our own proposed compressor, it actually gets better with more frequent uploads. This is our most recent result with this pattern-based GD, which is the big green line in the middle. It shows that it has very good compression regardless of the upload period. So it can be used both on the low end when we want to upload readings very frequently, and both on the higher end for other electricity providers who are okay with once or twice uploads per day. Another recent result from my research is this privacy issue that the legacy compressors have. So there is an open challenge from the association of basically electricity providers all over the world to try to quantify how bad this is and quantify how much information is being leaked by the compressors just with the compressed data size. So I took on this challenge, and I have a recent paper that gives a method of quantifying it and actually comparing both these legacy compressors, which are the TLMS ones and SEMA, against our own method. And I managed to prove that our own method is basically a better compressor and much less vulnerable to these privacy attacks than the built-in ones. My second project is what to do with the data once it's been transmitted. So basically, whether we can use or how we can use generalized deduplication, not only to reduce the data size during transfer, but also to store the data in this representation and run analytics on it, basically run queries on the data while it's still compressed. And generally, how this is solved is that data is split into smaller sections, and each smaller section is compressed separately. So when you need to decompress a part of the data, then you decompress that particular slice of it. But this is a compromise both on the compression rate, because there is less data that the compressor can work with, and also data access, because you can still not access byte by byte. You still need to decompress a whole chunk only to access the 2 or 3 bytes that you actually needed. So with generalized deduplication, we have a lot more flexibility and a lot more power than that. So in this project, I have designed a file format or a data format that enables us to store generalized deduplicated data and offer random access on top of it. And also I'm working on a proof of concept columnar database that uses generalized deduplication to store the data and also to run queries directly on the compressed representation. I won't really go into details. I think I'm running out of time. So the demonstrator here will be basically an exploratory analysis tool that runs in the browser. And what we can see here is kind of like a speculation or simulation. So the raw data size goes linearly with the number of IoT records. And our expectation is that the generalized deduplicated data, so the compressed data, is less than linear. So if we have, for example, a fixed memory limit of how much memory we can use for data analysis, which happens to be 2 gigabytes for a Chrome tab, then without any compression, we are able to work with 50 million records at a time. But with compression, if we store the data in a compressed manner and be able to process it in a compressed manner, then this goes up to around 150 million, so an order of magnitude almost. As I mentioned, I'm working on a proof of concept. So this is a little tool that can import a CSV file and compress it, keep it in the memory in the compressed representation, and then run SQL queries on it directly on the compressed representation, and compare the run times between the traditional non-compressed and the compressed query evaluation. Right, so as a summary, we have concluded that generalized deduplication is really well suited for IoT data and compressing IoT data. In the past bit more than 1.5 years, I have done, I think, significant steps to applying it to the power consumption readings. We have multiple compression methods that are new and proposed in this field. Also, we have taken on the challenge of the privacy leak that comes with the old compressors, also evaluated the new compressors, and looks like our solution is way better if we want to have much finer granularity of data uploads. So there's actually a good chance that this generalized deduplicated compression algorithm will be part of the globally standard, de facto standard upload protocol for smart meter electricity readings. Also, the compressed column store has a very good potential. It's an active research field, like basically all around the world in all kinds of database communities. And thank you very much. That was my presentation.